detecting the problem. So, when we are measuring these tests, we are going to apply the certain parameters. So, the basic thing that we are applying in all the test is strain, measuring the stress, okay. And we have to see, okay, if there is a noisy data, for example, okay. So, we have to understand whether you are measuring on a rheometer in the range of that rheometer, okay. That is the first thing. So, you should understand the range of your rheometer, what is the minimum torque that rheometer can measure, what is the minimum displacement that rheometer can really apply, okay. So, these are important things to notice. These are very basic things. I call those errors as cockpit errors, because those can be easily identified by the person who is measuring. So, when he measures, if he just looks at the specifications of the instruments and he knows, okay, if I am measuring now the first data points of this measurement, I am getting a lot of noisy data. So, first thing he should do is check the torque and see if that torque is really in the range of the instrument. Many times that torque is so low and it is almost either lower than the capability of the instrument or very near to this lowest capability of the instrument, okay. So, obviously you will not get a very good signal to noise ratio at this edges of the measurement. So, if I am measuring at very low torque or if I am measuring at very high torque also, okay. If I am measuring at a very high strains and if it is already taking to the maximum capability of the instrument, then also of course the data will not be good, it will max out, okay, it will saturate, okay. So, this is the first thing that you should always observe. You can see when we approach the low end area, okay, specifically we can see the signal to noise ratio is not bad and the quality of the data becomes bad, okay. So, always look at, first thing that you should look at is the torque values that are coming, and all the rheometers basically they look into they will have the facility to plot even the torque. So, you just can plot the torque in the table and look at the values, okay. And many of these rheometers will also tell you a certain status value like M minus, for example, that is indicating that the torque is too low, okay. If you look at a measuring point duration, okay, specifically if you look at a steady shear experiment, if I am doing at a shear rate of 0.01, okay, the unit of unit of the shear rate is reciprocal of second. So, 0.01 shear rate actually will require that event to complete will require reciprocal of 0.01, which is 100 seconds. So, physically that event will require 100 seconds to get over. So, if you measure over these 100 seconds, that would be the minimum, okay, for this event to get over. Plus you will also require a certain additional time, because physics is also there in the electronics, because electronics of the instrument, the mechanical properties, so the flow of data, all this is consuming time, okay. And this, when we are looking at microseconds, milliseconds, this time are also adding up, okay. So, we should, if you look at a measuring point duration, first 30% of the time is utilized to apply and that strain or stress that you have defined, okay. Then the next 70% is actually used to record the torque over the complete event, and then after that 50% of that time is used for averaging out the data, because you get a lot of information. The waveform is actually having 256 or 512 data points. So, 512 data points, let us say, of the strain, 512 data points of the stress, they are arranged, they are vectored, and then the phase shift is measured between them. So, all this, of course, this is happening very fast in the electronics, but still it is requiring few milliseconds to microseconds of time, okay. So, this all basically has to be considered when you are measuring specifically experiments, which, but of course, many times you would like to measure transient information. You would like to understand how this let us say if I am applying a shear rate of 0.01. So, from 0 to achieving 0.01, what is happening, okay. So, that also you can measure, Okay. So, that is the transient information. So, in that case when you are doing transient experiments, of course, you can take away this adjusting time, you can actually put the adjusting time to 0, you can actually put the the averaging time to 0, okay, and just use only the continuous recording. Okay. So, that is also possible, but if you want to do a non transient experiment, then of course, you will require to get the full, you will have to give this sufficient time to make sure this complete aspect of adjusting, recording and the application of the input parameters is done correctly over here. So, this is an example over here, you can see a example of a shear rate sweep. Okay, if you have a shear rate sweep starting from 0.01 in the transients, with very short times, you can see this banana curve, okay, which is happening. Okay. So, you cannot really get very good accurate low shear information at the lower side. Okay. So, of course, you can, if you want to measure transient, then only measure at 0.01 then and see how it is developing, okay, and then of course, record the final developed version also. Okay. So, this is what you should really understand. So, when you are setting these parameters of shear rates, okay, take care of the timings that you are using. So, if you are timing from low speed to high speed or low shear to high shear, okay, so you take a reciprocal of the time also. Let us say I am starting from 0.01 shear rate to 100 shear rate, okay, then I can start from the measuring time point of say 120 seconds down to 5 seconds or 1 second, because 100 shear rate will over in a fraction of a second, whereas a 0.01 second will require 100 second plus time. Okay. For oscillations and amplitude, whether it is amplitude frequency, generally we give no time settings, okay, but again that is a non transient experiment. If you want to still collect transient data, you can collect it at faster cycle times or very short time cycle times. In that case, of course, you can make this the adjusting time and the averaging time to 0, okay, and you can still get very good measurements done using that parameters. Temperature control, we have to always consider equilibrium times, okay, because the hardwares, the geometries can heat up very fast, okay, but your sample may not be heating up that fast. Okay. So, always make sure that your sample is following the temperature steps that you are giving. Okay. It is important to have the temperature control such that you do not have gradients in your sample. So, it is always better to have the heating or the cooling done from all sides of the sample. So, that is the reason only a flat plate may not be sufficient, you can also have a sort of hood on the top, or you can have a nice enclosed convection chamber, which basically makes sure that the heating is all around the sample and there are no gradients within the sample. Okay. The example of measurement between the same sample measured with a hood and without a hood, you can see a very big difference. It looks like two different materials altogether. Okay. Also, if you look at the equilibrium times from geometry to geometry, they are going to be different. If you have larger geometries like coaxial cylinder systems, you have to give much larger times because they have larger masses and the sample volumes are also bigger. But if you take a parallel plate, cone and plate, then you can marginally have smaller equilibrium times, because the volumes of the samples are also smaller and the geometries themselves are also not having that much high mass. Okay. So, the temperature to heat up the time to heat up the geometries and the sample will be much shorter in a parallel plate and a conal plate compared to that in a coaxial cylinder system, or if you are doing a measurement with a solid fixture, for example, then the samples are going to be quite big, 50 mm length, 40 mm length of samples and those will take of course more time. Okay. Even though the geometries in those conditions are not very big, the clamps are very small, but the samples itself are quite big, and of course they are mostly solid samples, so not flowing also. So, in a static condition, so the heating times and cooling times of those geometries of those samples are going to be also very slow. Okay. So, typically if you take coaxial cylinder systems or solid fixtures, temperature rates of 1 degree, 2 degrees C per minute, a maximum of 3 degrees C per minute are good enough. Okay. Don't go higher than that, but maybe for a parallel plate like a PP 08 or PP 25, it may be possible to go at a higher rate of 5 degrees C per minute also. The sample can still follow that. Can see the heating and cooling rates settings over here that can be done from the sample. Here we can see how the sample is following. The chamber is going very fast, but the sample is really not be able to take. So, if you have samples which are having very low conductivity, thermal conductivity, then definitely you will have to go to much lower heating rates than your sample. Also, the thermal expansions of these systems have to be considered. If you take the cone and plate, then of course you cannot do a coaxial cylinder, you cannot do a temperature sweep with a cone and plate. Okay. There is a possibility of course with special geometries, okay, which will have sensors in upper and lower geometries which can track the gap accurately, then we can even do a temperature sweep on the cone and plate. But these geometries are extremely costly and they are only, these sensors are only possible to be used in a limited temperature range. At very high temperatures these sensors are magnetic in nature, so they lose their magnetic properties, so then these sensors are not useful. So, if I am going to use within say 230 240 degrees centigrade, there is still possibility to do a cone and plate measurement with a temperature sweep using this type of geometries. So, always when we have taken care of the right geometry for the right samples, the right testing parameters, also understood what is really happening in the test, looking at the torque, setting the right parameters to get the torque in the range over there. At the same time, you should also take care of the basic sample preparation. So, when you are loading the sample, especially viscoelastic liquid samples, to make sure that there are no micro bubbles in the samples. The easier way to load the samples is to load it by volume if you are able to do pipette that sample, okay, because if you have liquid samples which are pipettable, okay, you can load exact volumes and you will not need to have any trimming. Every geometry will have a defined volume. So, you can easily take from any rheometer software, you will see that that software will be able to give you the sample volumes. Okay. So, you can load that, but of course, those samples which are not easily pipettable and you cannot really take them by volume, then you will have to put those samples first with a certain extra volume and then the extra sample will have to be trimmed off. Okay. So, this is something which is always important. So, if you have a correct volume, it is very easy to load, and when you visually see the loaded sample, make sure that you see a small bulge coming out of the sample, specifically when you are loading in a parallel plate or a cone and plate. Okay. So, the sample should not have a bulge inward like this, okay, but it should have a bulge something like this. Okay. The reason being, specifically if you take a geometry like parallel plate, the stress in a parallel plate is concentrated at the edges. Okay. So, if you have not properly loaded the sample, if there are the gap is, I would say, unfilled even in a small amount of place, the error that you get out of that would be very huge. Okay. So, it is very important to make sure that the sample loading in a parallel plate and a conal plate is such that the sample actually bulges out at the measuring gap, okay, at the measuring position over here. Of course, you will see that many times when you do a steady shear experiment specifically, because of the centrifugal forces, the sample actually can get contracted inside. Okay. So, that is the reason this extra bulge will also help you out if you are going to measure, like if you have an ink sample and you want to measure at a shear rate of 1000 second inverse. Okay, it is very important to have this bulk, so that when at this high shear rate of 1000, this ink is really going to go inside a little bit, okay, but it will still maintain that full gap condition even at that high shear range over there. Trimming the sample is important. If you take viscoelastic solids, okay, example asphalt, trimming is going to be one of the most important parameter, and if you are going to trim samples which are hot, okay, make sure that your trimming tool that you are using is also warm enough. Okay, do not take a cold tool and try to trim that. You are giving a very big thermal shock to the sample. Okay, if you are taking a very cold trimming tool and just directly trimming a hot sample, okay, so you just imagine what is happening at the trimming edge over there. Okay, so you have a sudden quenching of the sample over there, and it will also be difficult for you to trim with a cold trimming tool as compared with a warm trimming tool. Warm trimming tool will be easier to handle. Okay, this is an example of an influence of a bubble. If you have a bubble inside the sample, you can see it will act like a particle inside a sample. Okay, it will give you the same effect like a particle of the sample. And then of course the particle size, as we were discussing, if you have a particle size of say 10 micron, then the minimum gap that you should have should be 10 times the largest particle size. Okay, so always follow this gap. You do not try to measure very low at very low gaps just without the information of the particle size. Okay, because you will end up only grinding few particles and getting information of few particles. So that is not the real bulk information that you are getting out of it. Okay. Samples which are with dispersions or slurries, they would also require what we call as pre-shear. So the pre-shear basically makes sure that a sample is well homogenized before testing, and sometimes the pre-shear is also necessary if you take a coaxial cylinder system for example and you want to measure at say 135 degree centigrade. It is better to do a soft pre-shear to make sure that the temperature is really well stabilized across the whole sample, the temperature is really homogenized, and then you can do your viscosity measurements. Okay, so the pre-shear helps, it is a very good pre-treatment method over here. Okay, and then of course the torque range and the size of measuring systems. If you find that the torque that you are getting of this, especially the lower points, is quite low, okay, at 25 mm geometry for example, then you can immediately go for a 50 mm geometry that will automatically improve the torque at these small levels. Okay, so you can actually change the geometry size if you still want to measure at these low shear conditions, okay, and you want to have a much better signal to noise ratio. So definitely the size of the plate can help you very easily to get a good data out of it. At high shear, this is one of the things that can happen, specifically if you are measuring very low viscosity materials and you want to measure them at high shear, you get what we call as the secondary shear effect. The secondary shear effect is nothing but the material which was actually having a laminar flow, it goes into a turbulent flow. Okay, when it goes into a turbulent flow, the layers which were actually flowing like nice laminar sheets, these laminar sheets actually are crossing each other now in a turbulent flow, and that is causing that extra shear, and that is why you can see this viscosity increasing as a function of time. Of course, you can control this by the geometry condition to a certain level. So if you minimize the gap, you can push this non-laminar region a little bit further, but you cannot eliminate it completely. Okay, you can probably get to a little bit more high shear conditions without going into this turbulent region by taking smaller gap size, okay, for the same viscosity. The other factor that comes is the edge fracture, or we call it as a sample fracture in simple terms. if you have viscoelastic samples, when you are applying a shear on the samples, the sample also develop what we call as a normal stress, okay. And this normal stress is coming due to the Weissenberg effect. This normal stress will push the sample up, but if you have a plate there is nowhere to go. So, the only place to go is outside, okay. So, the sample actually starts leaving the gap, and when it leaves the gap it actually fractures, okay, and these fractures travel from this edge towards the center, okay. So, this is a typical thing that happens in viscoelastic solids, okay, because the elasticity high over there, the Weissenberg effects are more stronger over there, and when you go specifically into the non-linear region, you will see this normal forces strength increases more and more. So, the edge fracture effects will happen at this high strain non-linear regions, and we really need to know this where they are happening, because otherwise we start understanding that this is due to really the degeneration of the structure, but it can be due to the sample not getting hold inside the gap, okay. So, the sample is not filling the gap at all, and that is actually also causing the fall of the moduli, okay. There are certain geometries that can be used for I would say not eliminating this, but try to minimizing the effect of this or pushing again this effect to much higher strains, okay. So, there is a geometry which we call it as the cone partition plate, which is generally used for this. Then the other artifact that you get is the slippage between the samples. If you generally the geometries that we use very smooth surfaces, okay, and if you are measuring viscoelastic solids at very stiff conditions, they have the tendency to slip, so this geometry, when I say slip, the geometry is moving much faster than the sample, so they are not moving as a unit, okay. The geometry slips and it moves faster than your sample itself. So, the sample is nearly not getting the same strain that your geometry is applying, okay. So, that slippage again can give you this artifact. You will get a different torque out of it, and because of that a different stress, and because of that of course the different moduli or different viscosity. So, to counter that we can use geometries with surfaces which are roughened in a certain way. The roughening can be done by doing sandblasting, or it can be doing by doing profiling, okay. So, if you have very slippery gels, then profiling is good, but if you have very tough viscoelastic solids like rubber or asphalt at low temperatures, then we can use sandblasted plates over here. So, these are examples, typical examples of wall slip. You can see when you do a simple amplitude sweep from these, you can see this data, if you see these steps like this generally are occurring due to the slippage. You can also, if you have the facility to also record the waveforms, and if you see the waveforms also, the strains when the slippage is happening, the strains are actually becoming non-sinusoidal. You are actually introducing more harmonics into these waveforms, okay. This is the influence of the Taylor vortices or the turbulence. We have already discussed that, and we can actually reduce this, or I would say push this forward by adjusting the gap or lowering the gap, if of course the sample allows that. So, it depends on the particle size inside that. So, you can see the turbulent flow will generally cause an increase in viscosity. Many people say that this is shear thickening. No, this is not shear thickening. This is simply the physics which is giving us effect of high viscosity because of turbulent flow, okay. So, the viscosity of the material has not changed, okay. It is simply because of the non-laminar flow, the secondary shears are giving higher torques, and those are actually giving us the effect of high or increase in viscosity. Then you have the drying effects. So, if you are measuring emulsions or dispersions or suspensions, you can see the edge drying also gives us problems. So, if you have tests which are long, or you are doing at a little bit elevated temperatures where there is a evaporation of the solvent phases inside there. So, that can lead to again wrong interpretation of the data. You can see a moduli or viscosity increasing because of this edge drying, but it is not because of the sample, actually it is because of this drying effects which is forming a very fine film. And in parallel plate specifically what happens, this influences greatly because your maximum measurement is being done actually at this edge. Okay. So, it is important that if you are using a geometry like parallel plate and conal plate for samples with some volatiles which can dry, then it is better to use what we call as either solvent trap, or simply I can also, if let us your samples are water based for example, then I can actually load the sample and with a dropper add a very low viscosity oil covering at the edge. So, that also can almost minimize or make sure that the evaporation is really arrested at the edge over there. So, certain tips which are there. So, the solvent trap is one very good condition which can be used, or the covering the sample edge with the oil, that can help us. Then there are other possibilities, like if you are doing samples which are going to cross-link for example as a function of temperature or time. Cross-linking generally reduces the volume, okay, free volume. So, it contracts. So, you can actually use normal force to control and counter that. Okay. So, the normal force, if the contraction is happening, it will start pulling this geometry down. Okay. So, you can set a normal force of 0 for example, and it will, as the geometry gets pulled down, the rheometer will lower the gap to make sure that the force again becomes 0. Okay. So, that way we can control this because what will happen if you have a contraction of the sample, then your gap is unfilled. Okay. So, you are again now measuring with a unfilled gap, and this modulus that you are getting out of it is not correct. So, to make sure that the sample gap is completely filled at all times, you can use this normal force control to maintain the gap completely full by adjusting the gap during the test using this normal force control. So, this is very good way to make sure that any temperature compensation, any temperature expansion or contraction is compensated, okay, by using this normal force control. So, of course, this can be also used for bars. For bars also you will have the same. So, the bars itself will also expand or contract, okay, based on the temperature, and we can actually use a very small normal force to control this effect, and the change in length also can be measured as a function of this effect. So, you can actually as the with the normal force control, you see this gap changing as a function of the force, okay. To maintain that force, you can actually measure your gap as a function of temperature also. So, other simple effects, viscous shear heating effects at very high shear rate, the Weissenberg effect at like if you are using a coaxial cylinder system, you can see sometimes the sample climbing up the rod of this coaxial cylinder system. Okay, it can happen in only a coaxial cylinder system, not a parallel plate and conal plate. In parallel plate, conal plate, it leads to an edge fracture effect, but in a coaxial cylinder system, since it has a space to climb up, it will climb up the rod. Okay. So, this is typical for viscoelastic liquids to happen at, again it will happen in the non-linear region where you will start getting the Weissenberg effect. You can have other startup effects, transient effects when we are trying to measure at very short duration time. Always make sure that your rheometer is always upkept well. So, every manufacturer will have its own small way of making sure that the torque is very well calibrated for the geometries. So, these are certain tools one is basically the motor adjustment. In a motor adjustment, what is done is for every geometry, what is the residual torque across the whole 360 degrees is recorded and kept in the memory, and that is used also to actually when you are doing your sample measurement. So, this residual torque is actually subtracted from the sample measurements, so that you get the accurate values which are actually coming out only from the sample and not from the geometry. Okay. So, the motor adjustment has to be done at least every 90 days in general. If you can do every week or every day also, not a problem. It is a short measurement, you waste only 5 minutes out of it, but if you do it also every day, it is not a problem. You can do the measurements of the motor adjustments for all types of geometries, every geometries that you are using. There are geometries where if you are going to measure even the normal force, then you can do a motor adjustment for a longer duration of time at very low shear conditions, so that you can map not only the torque, but also the normal force at all 360 degrees. Okay. So, if you do a long adjust, it is actually mapping both the torque at the normal force, and if you do a short adjust, generally only the torque will be mapped over there. So, this is what is done, and always keep on tracking and recording the right inertia of all the geometries. Okay. So, these are the, I think so, two very necessary things that you need to do in terms of regular upkeep of the instrument, the motor adjustment and the inertia of the geometries. Okay. Both these things together will take altogether 5 minutes. Okay. So, you require to put your tool without any sample, do a zero gap, do one inertia and motor adjustment. Either way around, you can do a motor adjustment or inertia and motor adjustment, not a issue over here. Temperature calibration is important, it has to be done once in a year at least, and always cross check with either a standard oil or a standard reference material like a PDMS, which has certain known values. Okay. So, just to check that your measurements are really in the right place. Okay. So, this is something which also needs to be done on a regular basis. I would recommend at least once in 3 months or once in 6 months we should do the measurements. And then of course, other things which are important to look at, you are supplying air to these air bearings of the rheometers. So, the dryers of these air bearings are important. So, just keep on watching these dryers. There will be usually most of these dryers will have a color change as they get deteriorated. So, you should replace them, these filters which are there in these dryers can be replaced every once in a year or once in 2 years. You can look at the color changes, and also if you are using circulators or thermostats for counter cooling the temperature devices, then of course the liquids inside the counter cooling, those should be replaced very frequently, and the cleaning of this whole fluid path once in a year, once in a 6 month would be always necessary. So, that actually is about maintaining the instrument, maintaining the healthy condition of your rheometer. So, with this I would like to end the basics of rheometry. Thank you very much.